Good afternoon, Professor.
Good afternoon, Caroline.
Good afternoon.
Good afternoon.
Good afternoon. I think that was good afternoon, Caitlin. Good afternoon, Savannah. That was awesome. Good afternoon and hello and good afternoon, Amanda. And wait, and good afternoon, David K. And good afternoon, Alicia. Wait, and they're both wearing hats. Okay, whatever. Good afternoon, Amanda. They are sweet lids, I might add. Good afternoon, Jamalette. Good afternoon, Kevin. Sorry, yeah, I shouldn't draw attention to, and I'm wearing glasses. I'll now look at me. Okay. Wait, good afternoon. Hi, Christina. Good afternoon, Chloe. Good afternoon, Caitlin. Good afternoon, Elda. Good afternoon, Shamil. Good afternoon.
Good afternoon.
Nice, thank you. That was Amy, I believe. Yes, good afternoon. Thank you. I'm still thinking about that whole karaoke thing. Good afternoon, Adon. Did I say good afternoon? Good afternoon. Okay, no, that's a typo. See, now I'm commenting on people's spelling, and I thought it was okay. Anyway, good afternoon, David. Now I'm commenting on my comments. Okay, good afternoon, Sophia. Good afternoon, Felicia. I think that's okay. And we got Caroline, Kaylin, Amanda, Savannah, Elda, Shamil. I said Shamil. Amy. I said Amy. Kevin. I said Amy. I said Kevin. Christina. Elda. Right. Okay. Good afternoon, all. And not good afternoon, my board. I don't know what is. Hold on. You don't care. I know. I mean, you care, but you don't care about me caring. Hold on. I don't know why. So, okay. Oh, well. Okay. One more second for the board to maybe load. Okay. I'm going to give the board one more second to load. So listen. Okay. So I have this written on the board, but I'm going to say it anyway, and I'm going to put it in the chat in a second. I apologize. I do not have your exams yet. Maybe you already figured that. They're not in your Google Classroom. I am not done with them yet. I apologize. I was hoping to have them today, trying to. I failed. Obviously, it is a priority. You will get them back. You will get them back. And when you get them back, then we'll talk about the numbers. We'll have a chance to, there will be, not that the numbers are bad or anything like that, but there'll be a chance to make adjustments or get a little extra credit points or something like that. So don't, every day that goes by, don't be thinking that the situation's getting worse or something like that. It's not. But I know it causes anxiety not to have the numbers back. You will get them back. I'm going to say now, though, because I did fall behind, and there's no real, it's true that some of them are still actually not in, but I can't really, and that's making it a little bit complicated, but that's not really the reason. The reason is on my end, and the board is still loading, and it's not a good reason. I will admit, though, that because things have gotten clogged up, someone is screaming for me. Okay. Wait. Oh, hold on one second. Heal it. Wait, whoa, what's going on? Wait, stop. I apologize. Okay. That interruption has nothing to do with why I'm behind on the exams. I promise, sort of, and I'm lying. Okay, so I'm behind on the exams. You will get them. Every minute that goes by is more compassion on my end for your situation, believe me, and more opportunities that I'll construct to help you if you end up not liking your number, or if the number is like whatever, anxiety provoking, which I'm not saying it will be, but sometimes they are. Also, just for whatever it's worth, in the meantime, I didn't post the game turn yet for today. I will momentarily, but there's not going to be new homework sheets or anything until we get out from under this exam. I'm going to get back to new material in a moment. We're definitely going to continue with material, but extra outside assignments, you'll get a break from, and I'll get a break from grading until I get this exam back. That's like the least I could do, or it's whatever. It's something I'm doing. All right. So I apologize. Bear with me. You will get the exams. Oh, but one thing I was going to say, to be honest, because I failed to finish them for today, which had been my hope. I can't promise that you'll have them by Wednesday because Tuesday is my most clogged day. So just to be realistic, I don't want to raise false expectations. I'm trying to get them done. As soon as they're done, they'll be in your Google Classroom. Like, you know, we're not necessarily waiting for the next class period or something for you to get them, but they still might not be done by this Wednesday. And then of course it's the holiday, but I'll keep working through that. Anyway, I apologize. That's the way it is. It's not good. I'm now trying to get but we're going to continue with new material. And also in the meantime, in the background, obviously, if you have concerns about anything, like you're like, okay, but I understand, but I didn't get my exam back. So like, I'm worried about my status in the class or something, you know, you can text me or definitely come to office hours tomorrow. For example, last thing, sorry. You know, I am in my office a lot tomorrow. I mean, I have on and off meetings a lot as well, but I am there a lot. So feel free to please stop by if either to say hello or if you have concerns about anything. So I'm, you know, from 11 a.m. on for a long time on the 4th floor, that room, not my official office, my research lab on the 4th floor. I'll write it right now in the chat. Hold on. I'm still waiting for the board to come on, but and good afternoon. Sorry. Good afternoon, Sam, and good afternoon, Nicholas. Sorry about that. I'm going to write in the chat my office again, just in case there's anything, or my research lab where I will be. Because I always actually forget the number, to tell you the truth. Like, I know where it is, but bear with me. Sorry. Okay. That's just to be clear. If anybody just joins right now, you can write that down. Again, now I'm just trying to, so we're in a minute, we're just going to go on with new material. I'm just trying to get my board to work. I don't know why this is a thing. Actually, I do. Maybe know why it's a thing. And again, and please put any questions or concerns in the chat right now. I'm just waiting for the board to start. If it really doesn't work, I'm just going to teach without it, but I'm going to do one other thing while I'm waiting for the board to start. I do apologize. I'm restarting. Okay. No, admittedly, I'm stalling slightly on purpose because I don't know what's happening here. Really? All right, I'm starting my board all over. In a minute, I'm going to start without my board. I'm a little frustrated. And none of this, you guys were so sweet last Monday. Don't think I don't remember that. And then it was very touching. And I got text messages, very touching. Don't think I don't remember that. I do. I just wish my board was as touching and sentimental as human beings, although that'd be creepy. Okay. And I'm sure I've mentioned the Gus Johnson video. He was a YouTuber a few years ago before he got in some kind of trouble or put himself in some kind of trouble. And he was a very funny YouTuber that my older son, who's your age, introduced me to. And he does this satire of how to be a professor. And it's hilarious. I mean, he totally savages professors, but half of it is him making fun of professors standing in front of a room trying to operate the simplest technology in front of students, like not even on Zoom, like in real life, like just trying to open up like a YouTube, like from Google on a overhead projector and making a total mess of it. I mean, it sort of reminds me, it's like Michael Scott trying to do a PowerPoint presentation in an episode of The Office or something. It's absolutely hysterical. And what's really disturbing about it is it's so realistic. Okay. And of course, I'm a physics professor and I still can't, like, how many physics professors does it take to screw in a light bulb, for God's sake? Okay. Or turn on a computer. All right. I'm trying the board one more time, then I'm literally giving up. Don't think of it as giving up. Think of it as surrendering. Surrendering isn't losing, it's joining the winning side. Okay. So I'm trying one more time. And if Zoom asks me to re-sign in and prove that I'm me, just so that I can pretend to be me on Zoom, and then I have to remember my password in order to prove that I'm me, so that I don't accidentally take money out of my own bank account, which has no money, then I'm going to cry. Okay. And the only thing worse than watching a physics professor not be able to operate technology is watching a 52-year-old man cry in public over nothing. Okay, I feel the magic. I feel the magic. I hear someone welcome me. Am I going to say hello to me? Am I going to hello me? I see my ceiling. That's it. Or is that the heavens? It's so easy to confuse. Okay. Oh, I see two of me. That's just what we need in life. Okay. I think we're on. All right. I apologize again to everybody. And I feel like I have to, well, and now I'm frozen. Even better. Okay. 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 Good heavens. Yeah, that was worth everybody's time. We'll be sending you tuition refunds in the form of small Nintendo gift cards in the mail. They are totally redeemable for the new edition of Scarlet and Violet at any moment. Okay, okay. That's a joke, except you can't tell because it's not funny. Okay, here we go. Okay. Okay, we're going to start new material. Again, please feel free to put hate mail in the chat, complaints, questions, concerns. Well, weird. Okay, and the board is on a time warp. We're okay. Well, that reinforces that. Okay, this is the board. Okay, let me tell you what we're going to do. We're doing what we. Hi, Dan Yaffer. Nice to meet you. Okay, and all that was recording because yeah. Okay, here's what's going on. So again, this is the new material. Please stop me with any questions or concerns. When I say the new material, I mean the material is Newton's laws. We said the 3 Newton's laws like we stated them, we wrote them down, the 3 Newton's laws of motion. We stated them, we wrote them down last Monday. We have to start putting them into action now. Now, again, of course, I know that you started to see them in action already in a lab or 2, and probably that was a very confusing experience because you're seeing it in action before you're actually working out the theory. But of course, I should remind you that that's why this is a science class, not a math class, because that's actually how science goes. It's like we putter around and we play with the world and it confuses us. And then we try to work out a theory to explain our experience rather than the other way around. Either way is confusing, but I mean, so you have my total sympathy, but it's not an accident. So now I'm going to try to start setting straight some of the things that you've been groping around with in the lab about Newton's 3 laws, which are all about Newton's 3 laws of motion, which is all about the relation between forces and changes in motion. Quick last aside that I'll try not to turn into a rabbit hole. Remember, sort of the whole first section of this course, in a way, is just definitions and principles and meanings and concepts of motion, but specifically a lot of emphasis on the distinction between velocity and acceleration. And the whole idea behind the first part of this course is that velocity, raw motion at a constant, reliable rate of speed and a constant, reliable direction, all that is in the eye of the beholder, is a matter of perspective. Like how fast and what direction something's going and whether it's going at all entirely depends on who is doing the observing, right? Velocity is a subjective relation between 2 objects. One object can be moving at one rate according to me, but moving at a different rate according to you. So and it could be not moving at all according to Caitlin, right? Whether or not something's moving at constant velocity or at what constant velocity it's moving totally depends on the observation of a second object. That's the nature of velocity. But now what we're getting into now is that, and so objects don't naturally stop or naturally go at any particular speed, including even 0. They just, because what they're doing is a matter of perspective of a second object. However, what we're now, so the natural state of an object, according to Galileo, and according to everything that comes right up to Newton, the natural state of an object is just to maintain constant velocity, whether that velocity is 0 or something else. The natural state of an object left to its own devices, left alone, would be to not change its velocity. But then we say, okay, for an object to change its velocity, for an object to accelerate, requires the intrusion or the influence or a force being exerted by some second object. So the large scheme of Newton now becomes, at any given moment, if we look at a single object and we look at all of the forces acting on it from other objects, if we could somehow identify and quantify and combine all of the forces acting on a single object from a bunch of other objects, from whatever other bunch of objects are interacting with it, if we were somehow to be able to identify and assess all of the forces acting on one object from other objects, then we would know at that point in space and at that point in time, we would know the instantaneous rate at which that object of concern would accelerate. Okay, the whole, and once we know its acceleration, once we know its instantaneous acceleration, then we kick in all of the knowledge and all of the definitions and all the equations and all the principles and practices that we've established in the first part of this course, in the first section of physics. Okay, so the program now is, if you know how other objects are interacting with a first object at a point in space, at a point in time, then you'll know the instantaneous acceleration of that object. You'll know how it's going to change its velocity, how it's going to change its state of motion, and then you could predict its motion and its space and time coordinates for all points in the future and all points in the past, if you're, for example, solving crimes. So the whole program now is that forces yield accelerations. So the real, absence of forces yield constant velocities. Sums of forces, net forces, yield accelerations. So our program now is to be able to identify forces on objects in order to calculate their accelerations and then kick in everything we already know from the beginning of the semester. That's the program. So really, so we're going to use, so the first of the three laws is just the state of affairs that describes everything we've done till now. And it's the second and third laws of Newton, most particularly the second law, that we're going to use to really quantifiably predict accelerations of objects. The way we're going to do this is through diagrams. There's two different types of diagrams that I want to develop today. Again, that you might have been sort of like thrown into the deep end of using in the lab, and you may have been forced to like look them up on the web or something like that. But I'm going to try to enumerate now these two different diagrams, two different modes of diagramming forces, and thereby predicting accelerations. Okay, so what FBD stands for on this sheet right here, I mean, on this board, it says, well, you can't even read that, but it says FBDs. FBD stands for free body diagrams. That's what I want to show you how to do today. Even of free body diagrams, there's two types. I hope to get to both types today. But even before, I should even say, even before FBDs, there's something else called SSs. Okay, so you may want to make a note of this. I know this is all like overly. So first we're going to do SSs, which are system schema or schemas. Okay, then we're going to do FBDs, free body diagrams. And there's two types of free body diagrams. There are pure free body diagrams, and then there's component free body diagrams. The goal of today in principle is to get to all of these, okay, and show you how we use these ultimately to, this is all about really Newton's second law of motion, which is to say, okay, just to give you perspective again, especially because why not? Like the law that mathematically generates sort of the rest of physics, the law that mathematically generates all the information that we sort of use in the rest of physics is Newton's second law, F net, or sum of the forces equals ma. And so the whole idea again, and I know I mentioned this last Monday, is that if you add up all the forces on an object, if you add up all of the forces acting in a certain axis on an object, then you will get the acceleration of that object on that axis. Like F net equals ma is a vector equation. So it's really true simultaneously yet independently along three axes of space. But the idea is you add up all the forces, you get the acceleration. Well, everything I'm going to do today, and maybe also Wednesday for a while, all the action comes in trying to figure out what are all the forces acting on an object and in what direction are they acting and what are the numbers for them. In other words, all of the hard part, all of the thinking of physics comes in trying to establish what to plug in to the left side of F net equals ma. It's all of our thought goes into what should go into an expanded version of this left-hand side term, sum of f's. So the way we find out what to plug in for all the f's that will add all up and divide by m to get a, how we figure out what all those f's are is through diagrams, like sort of one stage at a time. We do a system schema, then we do a pure free body diagram, then we do a component free body diagram. And from that, we know what to plug in to the left side of Newton's second law. And from that, we infer acceleration. And from acceleration, we go back to all the old material in this class. So that's the program, okay? Along the way, we're also going to learn about some specific forces, such as the force of weight. That's what it says on the side. So, okay, so let's get going here. Okay, so the program is what I just said. I just wrote it down, right? So the whole program is solving F net equals MA, off generally to solve for A. So the difficulty comes in figuring out what sum of F is. So in order to do that, we're going to make a series of diagrams. And that's, again, that's like the focus of now for the next 45 minutes. I'm going to start, I mean, the very simplest scenario at all would be no forces acting at all. No forces on the, we mean zero on the left-hand side, and zero would yield zero acceleration. That's the first law. Okay, that's what the first law takes care of that. So we don't need diagrams or much thought for no forces. So what's the next simplest scenario we could look at? The next simplest scenario we could look at would be like one force. One force acting could be, for example, the force of gravity from the center of Earth, pulling down an object so that the object is in free fall. Remember, the definition of free fall doesn't necessarily mean something's moving down, but it does mean, from earlier in the semester, free fall means no influences, i.e. now no forces acting on an object other than the one force of Earth's gravitational pull. Whatever that gravitational pull, like whatever, you know, and all I know about the gravitational pull right now so far is that it seems to exist because things seem to drop when I let them go, right? So I'm going to analyze this one force scenario known as free fall. And I'm going to analyze it according to diagrams and stuff. Okay. So Okay, I'm going to read this. What I'm doing right here. I mean, this is maybe a lot. I don't know. So we're going to look at free fall now. We're going to draw a bunch of diagrams representing free fall. We're using free fall as an example of how to draw these diagrams in general. I'm going to give you the rules of how to draw these diagrams, and their rules in general. We're going to apply them to free fall, but they are general rules. So first, I'm telling you how to draw a system schema. And obviously, I'm going to draw it in a second. But the whole idea of a system schema is, first of all, you draw in a system schema. It says we represent our mass, our object of concern, by a dotted circle. So we're going to draw one dotted circle somewhere on the page to represent the mass that we're talking about here. So here, let's imagine there's a tennis ball that's in free fall toward the earth, or a bomb, or whatever, or a brick falling toward the surface of the earth. So we're going to draw a dotted circle to represent the mass that's in free fall. Then, for any system schema ever, we draw one solid circle for every single mass in the world, every single mass in the universe that we believe to be interacting, exerting a force on, interacting with our mass of concern. We draw a solid circle for every object in the world that's pulling or pushing on our mass of concern. Okay, okay. I'm going to give you one more rule, and then we're going to do it here for free fall. So tell me if you want me to turn back a page. Okay. This is all a little bit, this is all pretty abstract sounding, but it's all rules for drawing concrete diagrams, which we will do in a moment. But I'll just read for handwriting's sake or whatever. What this says is, it says, see, between each solid circle and our dotted circle, we draw a solid line. Okay. So we're going to have a dotted circle in the center of the page, somewhere in the page, representing the object that we're looking at, the M, the mass that's going to accelerate with a certain rate. And then we're going to draw a solid circle for every object in the universe that we believe to be pulling or pushing our dotted circle. We're going to connect every solid circle with our dotted circle by a line segment that's going to connect the two objects. The line segment is going to represent that interaction, that pull or push, or i.e. that force. Okay, so that's what C is saying. Then D, and here's like the weird part, and obviously I'm going to show you in the pictures, so I shouldn't say obvious, nothing is obvious, but D says our connecting lines will follow the one touch, one line rule. That is where we're going to find, so we're going to start with a simple diagram that's just a free fall. But, okay, pardon me for one second. I hear, pardon me for one second. I'm coming, but Felix. Okay, sorry. Thank you. So our lines are going to follow this one touch, one line rule, meaning that every line we see in the picture should represent one touch in the universe, like two objects touching each other, like literally, and vice versa. Anywhere in the universe we think something is touching our object of concern, we should find a line. But there's going to be exactly two exceptions to this rule. This rule sounds really crazy. It's like a rule that I'm right away giving you two exceptions to, but let me be clear. It's rigidly exactly two exceptions, and the exceptions are almost as important as the rule. Okay. And you're going to see again in action in a second. But the two exceptions are the line that represents the gravitational pull from planet Earth, or from the center of Earth, and we ultimately are going to call that gravitational pull the weight of an object. And whenever two surfaces are pushing on each other, there's going to be an exception to this rule. Now, I'm going to get into those exceptions momentarily, but I want to start doing this. I know this is all very abstract right now. The reason for all this, just bear in mind at all times, try to bear in mind at all times, the reason for all of this talk and these rules and this diagram is because the concept of Newton's laws is, as long as you know exactly what all the forces are doing to an object at any point in space, in any point in time, as long as you know all the as long as you know all the forces acting on an object, and as long as you can literally quantify them, like you actually know the force vectors, like as long as you know the magnitude and the direction of every force acting on an object at some point in space, at some point in time, then you will know the acceleration of that object at that point in space, at that point in time. So the whole, and that's a simple equation, F net equals ma. As long as you know the sum of the F's, then you'll know the A. And let me remind you again that as long as you know the A, you just run all the equations that you just got tested on. And then you know everything, then you know exactly where the object's going to be at any future moment, or you know when it'll be at any requested space. Or you can run back in time, solve crimes, and know where the object was at any given moment. So it's all about, the first half of this course is all about knowing A. The second part of this course is all about how do we find out A from all the F's. So the tricky thing in physics, and I mean for physicists and for physics students, like the tricky challenge is, what are the F's? How do we know what the F's are? And how do we know what they are at all? And specifically, how do we actually know their magnitudes and directions? So all these rules and all this diagram, like abstraction that I'm trying to give you right now, is all a breakdown algorithm for being able to know exactly what the forces are doing without having to know in advance. It's all a method for, like, once you think this through, for us not having to think or question or be confused, and just be able to follow a procedure and know what the forces are acting on an object. Okay, so the first way we do, so it first comes through drawing this system schema, and all this business about one touch, one line is all about knowing what lines to put in and what objects to put in. So okay. So these are the rules for a system schema. They sound weird right now. I think even to me, they sound weird right now. But now I'm going to start showing you them in action. And maybe I'll do a couple examples. And then we'll go to the free body diagram pure. And then we'll go to the free body diagram component. They all get built one from the next. or one from the last. All right, so these are the rules of the system schema. So example, free fall, right? So I'm going to start with, let me be more specific, free falling mass. Okay, so M stands for some mass that is falling, that is in free fall toward the surface of the earth, like a tennis ball or or a bullet or a bomb, whatever example. You ever notice that all the examples from physics are like about war and sports? Kind of alienating, right? Like even I find that alien. I mean, is that a gender? I don't know. It's very strange, but it's historically the way it is. Anyway, so let's instead example a stuffed pink, whatever. Okay, so example like a tennis ball. On to Earth. Okay. And by the way, one fact we do know, I'm not going to use it quite yet, but let's just try. What's also a given is if something is falling, if something is in free fall toward the Earth's surface, we know that the acceleration would be a constant, right? And we know that that constant would be called g, like whether it's like 9.8 meters per second squared, or we round it to 10 meters per second squared, or if it's on the moon and it's 1.16 meters per second, we call it lowercase g, just to remind you that. Except, okay, so what would we do? We would first draw a dotted circle that represents this mass. So we have a dotted circle and it's labeled M. Okay, that's our tennis ball that's falling to the earth. And there's always some M that we're focusing on in all these problems. Now we're going to draw, sorry, that was a dotted circle. Now we're going to draw a solid circle for any and every object that we think is interacting with this one, i.e. pulling or pushing this one. Okay, now this one is falling toward Earth. It's being pulled toward Earth. I don't exactly know how gravity works, but I know that it does. Like I know whenever I let things go near the surface of the Earth pulls on them. So I know that somehow planet Earth, or the center of Earth, is somehow pulling on this object. So I'm going to draw a solid circle to represent Earth, or represent, and all my objects will always be circles. I mean, it happens that Earth is a circle, but that's like not the reason. So I'm going to draw a solid circle somewhere, okay, over here, anywhere on my picture, a solid circle. And this solid circle represents planet Earth, or you might even a better thing to say in a way is center of Earth. So I'm writing CE for center of Earth. You could write PE for planet Earth. But the reason I'm not just writing E for Earth is I'm trying to make it very clear right now that I don't mean Earth like dirt. And I don't mean like the ground. I don't mean the floor. I mean like literally like the planet. In fact, specifically, I mean the center of the planet toward which everything seems to fall. Again, I'm not claiming I know why. I just know that somehow from experience, like that somehow the center of planet Earth seems to pull everything toward it. Okay, so I'm drawing a solid circle to represent the center of Earth. Okay, and then I'm asking myself, is anything else interacting with my tennis ball? And if it's in free fall, the answer is no. If it's literally free fall, like you might say, well, like, what if someone's touching it, or what if someone's like holding? Well, then that's not free fall, right? Or you might even say, what about the air? And the air can affect certain things, like a piece of paper floating, or like a parachute, but then that's not free fall, right? Free fall is when you're literally only being affected by center of Earth. So I know, so I've chosen this example on purpose. There's only one solid circle in my picture besides the dotted circle, okay? And I'm going to connect them with a line according to that rule. According to the like connect everything with a line thing, okay? Now, this is a relatively simple example, so it's a relatively simple drawing. The only thing in the drawing or in the scheme is I got my dotted circle, the one that I'm going to be analyzing, and I've got the one object that's affecting it or interacting with it, that's exerting a force on it, called center of Earth, and there's one line between them. Now, what was this whole, and that's it. That's the whole picture. That's it. Okay, that's the answer. We're going to do something with it in a minute. You're going to see the purpose of it in a minute. But first of all, that's the answer. That is the system schema. Bless you. This is the system schema for free fall. Oh, and I could do one other thing too. Well, wait, no, I'm going to leave. That's the picture. Notice there's one object of focus. There's one object interacting with it, center of Earth, and there's one line between them. And the one line between them represents a force. This is a force. It's a force that's being exerted by the Earth onto the mass by Newton's third law. It's also being exerted by the mass onto the center of Earth. This is known as the force of gravity exerted by the center of Earth, or the more common word that we use for the force of gravity being exerted by the center of Earth on any one given object. The common word for that is weight. This one line represents the weight of our mass. Notice that, so the ultimate purpose of this diagram you're going to see is the lines. We start by drawing the circles, and we connect the circles by the lines, and each line is a force of some kind. Notice the way we're, and of course, this is meant to be simple at first. It might be so simple that it might even be confusing you as to what's the purpose. But the purpose is ultimately every line, we draw this kind of system schema in order to generate lines. And each line is a force. We're trying to figure out how many forces are acting on our mass. In this case, the answer is one line is acting, one force is acting on our mass. But you notice the way we constructed this diagram is we didn't have that line until we had two objects. Part of what this diagram is trying to reinforce is forces never come from nowhere. Forces never come from nowhere. A force is always an interaction between two identifiable objects. You can't even say that there's a force or start doing any math with a force until you identify two objects that are interacting via that force. A force is an interaction between two objects. So I'm going to go on. I still haven't explained what I mean by that one line, one touch rule, but one thing I'm definitely saying now, I'm definitely saying this. Each line in an SS, in a system schema, is a force. Each line is a force. If there's 5 lines in the system schema, then there's 5 forces acting on the object. And that's our real purpose of the system schema, is to figure out how many forces are acting on an object. I'm going to give you another example before. I'm going to give you 2 more examples, actually, before I go on to free body diagrams, to whatever extent I have time. Hold on. So example 2. Okay, in example 2, let's say, so this is the, like, so let's say we have a fish hanging from a fishing line now. Okay, so it's hanging stationary. So that's our example 2, and I want to draw a system schema of the fish. And let's say the fish is of mass m, a fish mass m again. So I want to draw the system schema of this. This is how this one would go. First of all, I have my dotted circle to represent. Like that was just a picture, what I just drew up. Like, that was just a picture. It would be like step 1 DFP. That was just a picture to show you what I'm talking about. But now here comes my diagram. I draw a dotted circle to represent M, the fish. Then I'm supposed to draw a solid circle for every object interacting with the fish. Okay, the first thing I'm going to do is I'm going to draw a solid circle representing the center of Earth, because I think that the center of Earth is pulling on every single object that at all, period. I think all objects are being pulled toward the center of Earth, whether you let them go or not. They're all being pulled, right? Which is why, even this pen right now is being pulled to the center of the Earth. When I let it go, I'll see that in action. Right now, I'm fighting the center of the Earth by holding it up with my hand. Well, that's exactly what I'm about to say about the fish. But the point, I think all objects are pulled by Earth. Earth is always there. It's always pulling on objects. So I draw the Earth somewhere in my picture. I could draw it the same place I drew last time. But I could draw it anywhere. I'll draw it over here. Here's a solid circle representing center of Earth. It's always there. But now, but that's not the only object interacting with the fish. That object is always there. So please make a note of this, maybe, if you're still with me. Like, the center of Earth is in every single system schema, definitely. That's why we start with free fall as an example, because Earth is always there. The thing about free fall is it's the one example where Earth is the only thing there. But Earth is always there. So it's in every system schema. But then, the rule here, or the idea here, is I'm going to draw a solid circle for center of Earth every single time. Then I'm going to draw a solid circle for every single object that is touching my M, my mass, my mass of concern. Every single object that's touching. This is where that weird rule about one touch, one line starts to come into play. Anything that's touching it. So I look in my pic, oh, there's a line, there's a string touching the fish. So I'm going to draw a solid line somewhere. I don't care where. This has nothing to do with direction or location. I'm just going to draw a solid line somewhere for that, to represent that string. And that's it. Now that's, sorry. Okay. Thank you, direct chat person. I see. Hold on. I see. Cool. Thank you. I appreciate it. Yeah, cool. Thank you, direct chat person. All good. All right. And they're gone. So I draw a solid circle representing the string. Notice the string is a physical object. It has its own mass, probably. It's its own object in the world that I'm now caring about because I see that it's touching my fish. So I'm drawing everything that's touching my fish, everything that's touching the mass. I'm going to draw. Plus, I'm always going to draw a center of Earth, even though it's not touching it, but it's always there. So now I'm going to connect with lines. Okay, this is now, we're done. This is the system schema for a fish on a line. Now let's look at this for a second. This picture has 2 lines in it. That's the purpose of the picture. One line is the force of gravity, which we call weight. The other is the force, the pulling force being exerted by a string on the fish. Okay, it's coming from a string. The object that's exerting the force is a string. the interaction itself, the name of that force, the name of any pull that's exerted by a one-dimensional object, such as a string or a rope or a rod, that force is called tension. Now note, so what we're saying here is that if there's a fish, if there's a fish being held up by a string, then there's two forces acting on that fish. One is called weight, the other is called tension. But notice the conclusion that the diagram is sort of trying to show us is that when we start plugging into the math, we'll have two forces to plug in. One we're going to call weight, one we're going to call tension. But notice where they came from. They came from two objects, an object called center of Earth and an object called string, right? So the purpose of the system schema is it generates lines that we are going to use as our forces. We're going to name these lines and then put numbers to them and plug them into equations. But where the forces, how we knew what forces are there is we first drew object. We can't have a line without some circle interacting via that line. And notice that it's a line. It doesn't have arrows on it or anything. So what it's trying to also connote is if we believe that some string is exerting a force of tension on a mass, then we believe that the mass is exerting a force of tension on that string. Like it's Newton's third law. It's symmetric. But there's two forces being connoted by this object. Now start to see also what I mean by the one touch, one line rule. What I mean is that for every line in this picture, there's a touch, like with exceptions. Like there's one line representing tension because we have one object touching the mass, known as a string. One line, one touch. Put another way, how do you know how to draw the lines? You draw everything that's touching your object, but exception one is first, is gravity. Exception one, or exception A, or whatever, to the one touch, one line rule is that gravity always gets aligned. Weight, the gravitational pull of Earth, always gets a line in your drawing, but there's no touch. Gravity is an exception to the one line, one touch rule, because gravity is an exception. It's an exceptional force. It's a force that seems to happen without touching. But what I want to emphasize is it's always there. We wouldn't even put it in diagrams if we didn't. I mean, it's really mysterious that gravity, that the fact that center of Earth can pull on all of us without touching us seems to go against what every single other force that we would ever put in these diagrams ever does. In every other case, if you want to know whether a force is happening, you have to ask, is physical contact happening? But gravity is the one that just seems to be always there without physical contact, but it's always there. So we put it in first. We always put in center of Earth right away, and we draw a line before we do anything else. And we know there's always going to be this one line, this one force that seems to happen without touching, so it's an exception, but it's always there. And then we go on, and if we're trying to figure out what other things are acting on our object, we ask what other things are touching our object. So it's gravity first, and then anything and everything else that's a touch. That's almost entirely what I mean by this one line, one touch rule. But now let me show you the other exception, and then we'll, whatever time is left, we'll move on to the other diagrams, or we'll wait till Wednesday. But I'm going to give you a third example now of a system schema, just so you can see the both exceptions, and then we'll be okay. The other exception is, so example 3. But again, stop me or tell me to go back a page. Sorry. Okay, so this is now example 3. It's getting closer and closer to what you might be picturing from lab. Say we have now a block of wood or an eraser or something like some kind of like rectangular, like blocky object that's on a horizontal surface, an horizontal tabletop, and it's like sliding along. Maybe, yeah, sorry, it's sliding along. Why? Because someone pushed it like a minute ago, like someone gave it a nudge, an initial velocity, and so now it's on its way. It's like something that's falling, only it's not falling, it's sliding on a horizontal tabletop. And maybe it's slowing down if that's easier to picture. Maybe it's eventually going to stop, but right now, I mean, it probably is slowing down, but right now it's just sliding at some velocity and maybe some acceleration. And it's on a tabletop, and it's a rough, realistic tabletop. Okay, so we've got an object on a tabletop, and the object is like flat faces, and the tabletop is like flat. Okay, so it's like not meant to be a trick. And we want the system schema of this. Okay, so that's the situation. We want the system schema. So we start with a dotted circle, which represents our mass, our object of concern, right? And then we go in order. First, we say, okay, center of Earth is always there. It's always pulling on every object. Every object has weight. Every object has weight, whether it's falling or not. So we draw some, and notice I'm drawing center of Earth wherever I want. I'm in the system schema. All these objects are drawn like around our object of concern, but like wherever we want around it. That's sort of like we're okay. So I draw center of Earth wherever I want, and that's a solid circle. Okay, and I'm going to connect with a line, and that's called weight. Then I say, okay, so then I ask, all right, that was center of Earth. That's always there because it always is. Then I say to myself, what's touching my mass? Oh, and I see there's a tabletop that's touching my mass. Okay, so I draw a solid circle somewhere, wherever I want. I don't care. And that represents the tabletop. Okay, now it's touching the mass. So that means it's interacting with the mass. It's like pulling or pushing the mass somehow. So I'm going to draw a line, right? Now, here's as hard as it gets, this is the second exception to the one touch, one line rule. Remember, we said there's a one touch, one line rule. For every touch, there's a line. Conversely, for every line, there's a touch. But there's 2 exceptions, we said. Exception 1 is gravity or weight. That's always there. There's always a line representing gravity, even though there's no touch associated with gravity. So that's exception 1. Super important. It's always there, right? And again, remember in the back of your mind, why I'm even concerned about all this is I'm trying to figure out what forces are acting on an object at any time. What I'm really trying to say is if you want to know the forces acting on an object, ask yourself, what are the things touching the object? Only always remember, once you ask yourself that, once you say, what are the things touching an object, that there's 2 exceptions to that rule. Like the rule is a touch is a force is a touch, but there's 2 exceptions that are super important. And again, only exactly 2, not sort of 2, exactly 2. So exception 1 is gravity will always be there as a force. Weight will always be there as a force, even though there's no touch. Okay, we got that. And then the other exception is whenever we see 2 surfaces pushing on each other, pushing, like gravity is a pull. To pull is to bring toward. Earth pulls me toward it. That's a pull. But when things shove each other away from each other, we call that a push. Whenever 2 surfaces, 2-dimensional planes are pushing each other, that's the other exception to the one touch, one line rule. Now, before I even tell you what the exception is or what you do with it, I'm reminding you again, remember in the other example, in the string pulling the fish, that was not an exception at all. That string exactly followed the rule. There was a one-dimensional thing called a string or a rod, and it was pulling on a fish. It was one object touching a fish. It got one line for that pull, right? In the other diagram, the string got a line. End of story. Here, Cool. I love it. It's like it's like the only interruption to my mind that actually works. I know that's not true. All of your, but all these other things happening in my house. I'm getting all these. Okay, we'll see now. I'm going off. No, I love it when he does that. I'm sorry. I'm sorry. It's just making me cry. But okay, cool. Okay, cool. So it makes sense. So hopefully, the one person. But part of why I love that is like, even if he's lying, I'm not saying he's lying, but the fact that he knows exactly the right moment to say that means something does make sense. You know what? Anyway, it's called EQ, emotional, whatever. All right. No, and it doesn't interrupt my flow at all, right? See, I'm totally exactly not at all in. How many ADHD professors does it take to go, oh, there's a light bulb? Okay, no, all right. So, here's the exception. Two surfaces are pushing against each other. The tabletop is pushing against the block of wood that's sliding on it. And or Newton's third law, the block of wood is pushing on the tabletop. Whenever you have two surfaces pushing on each other, as we do here, then we draw two lines. Okay, that is unexpected, perhaps. That is a little weird. That's why I'm making a big deal of saying it. I'm saying it's the one other exception. So now I'm backing off. Oh, well, let me say, this is our diagram now. I mean, I'm going to put in some words in it, but this is our diagram of an object sliding across a tabletop. We actually get three lines here. And by the way, the fact that there's three is not because the thing is moving as such. Like, even if it were sitting still, technically, to be honest, even if it were sitting still, I would have three lines here, even though that's a little bit harder to picture. But what's the deal with my three lines? Like, what's the deal with why? So I'm saying now, if you have two surfaces pushing against each other, rather than two objects pulling at each other. So if you have two-dimensional push, rather than say one-dimensional pull, then you draw two lines. And the reason for that is that, especially if the two surfaces are rough, which maybe I should even put into the rule, especially if the surfaces are rough, the reason I have two lines is because when two surfaces push each other in the real actual world with real actual rough surfaces, for a tabletop to push a block like this, if you were to look at these rough surfaces, like if you were to zoom in and look at them microscopically, you would realize like that each surface is like bumpy, ridgy. It's like the nooks and crannies of an English muffin, or like the teeth of a comb, or like a little mountain range, each surface. And so when two surfaces push together against the plane of contact like this, they also automatically lock into each other and cause like a rubbing or sliding resistance along the axis parallel to the plane of contact. When two surfaces push, and I know it's like 3 minutes left, so we're not gonna go to the other diagrams today. It's fine, but just so you, but this is like actually a lot in itself. I'm saying from here on in, especially when two rough surfaces push against each other, they push against, but they automatically also pull along because they get locked into each other. The pushing against is called normal. Normal means perpendicular. Perpendicular to what? To the plane of contact. So if these are like two slices of bread, the bologna in a bologna sandwich, the bologna, does anybody eat bologna anymore? If it's like two slices of bread in a bologna sandwich, the slice of bologna in between is what I mean by the plane of contact. If the sandwich is like this, the plane is horizontal. If the sandwich is like this, the plane is vertical. The extent to which the two forces push against that plane, perpendicular to that plane, we call normal, because not because it's typical or average or regular or anything, but in math, normal means perpendicular. And the other component of push that automatically kicks in because the surfaces are microscopically ridgy, or is the rubbing, sliding resistance that occurs is what we call friction. And friction will always accompany, a frictional force component will always accompany a normal force component whenever rough, realistic surfaces push together. Not when they pull, that would be like magnets. Not when lines pull, that would be like tension. But when surfaces push, we get a push along one axis and another automatically. So friction is the force parallel to the plane of contact. So we're just about done. So this other line would be called friction. So notice the tabletop is exerting. So I'm ultimately saying if the tabletop is pushing again, is touching this block, it's ultimately touching it in two transverse ways. A way that we call normal, that's the push against, and a way that we call friction, that's the push along. So notice this diagram has three lines, three forces. Right. So the bottom line is in every, we're going to stop here. I see it's 1:30. We're going to stop here, but just this is the full package of system schemas. In a system schema, you always draw a solid circle that represents planet Earth, center of Earth. Then you draw a solid circle for every object touching your original object. And then you go around and make sure you have one line for every touch, noting that with gravity, there's an exception. There's one line, but there's no touch. And with surfaces pushing each other, there's one touch, but there's two lines. As long as you follow that rule, you will have a system schema. At the end of the day, every single line in that system schema will be a force. And then what we're going to do is from that system schema on Wednesday, not now, we're then going to take that system schema and every line from the system schema we're going to turn into a vector arrow in something called a free body diagram. And from the vector arrows, we'll do math. So we draw this to generate the exact correct number of lines, each line ultimately representing a force, all to be plugged into the left side of F net equals MA. You've been very patient. You've been very tolerant. I really appreciate it. You're also very sweet. And you understand everything. And that's the other good news. So thank you very much. And I will see you Zoomily on Wednesday or maybe tomorrow if you visit. Okay. Sorry. Thank you guys very much.
Thank you. Bye.
Oh, that was even a fate. Oh, thank you. Bye. Awesome. Okay. Awesome. Okay. Awesome. Okay. Bye. Bye. Thank you guys. I appreciate it. Okay. I'm going to turn this up. But you guys are good. Like Shamil, Alicia, Samuel, Amy. I know I still well, you guys, I owe you things, but thank you. You got me things. I appreciate it. I know it. I'm stopping the recording.